Okay, so we are now going to have the seminar part of this session, and it is my great pleasure to welcome Dmitri Efetov, who actually flew all the way from the US to be here today, so thank you, Dmitri. Dmitri is one of the leaders worldwide in experimental studies of Moiré systems, and especially twisted bilayer graphene. And his talk will be a review of this. I'm very grateful that he accepted to give us this overview. Let me tell you a few things about Dmitri. I believe he did his PhD at Columbia University with Philip Kim, who is another big name in graphene physics and in this field. Then he moved for a postdoc and had his first faculty position at ICFO in Barcelona. He then moved to the Ludwig Maximilian University in Munich, where he is up to his day and has built a very nice lab there that I had the opportunity to visit, I don't know, a bit more than a year ago. And he got many distinctions. I'm not going to embarrass him by quoting all of them, maybe just one, the Leibniz Prize of the DFK. So Dmitri, the floor is yours. Thank you so much.
Okay, thanks very much, Antoine, for the invitation. That's my first time in Collège de France, so I'm quite impressed with the history here. Basically today I just want to really give you a little bit of a sort of broader overview, an introduction about Moiré materials, and also in the end I'll try to also give a little bit of an outlook where I think we stand and where we're probably going in this field. And so just to really start slowly, so this is a STM image, scanning tunneling microscopy image of such a Moiré material. So those are two layers of bilayer graphene stacked on top of one another. And you can recognize the graphene part by this small periodicity here, which is sort of the honeycomb lattice with the small periodicity, which is the individual graphene layers. But those two graphene layers, they form this interference pattern, which you see as this larger scale periodicity arising. And so this gives, for example, a very large density of states in these larger unit cells, as you can see here, resolved by STM. But overall, I will try to sort of convince you that this Moiré superpotential really has very strong implications on the electronic band structure of the material and also on the topology of the material. Okay, so and with this, basically some sort of comparisons with twisted bilayer graphene have been sort of made, which sort of position it sort of in the strongly correlated quantum materials platform. And basically the comparison that one can sort of draw here are the phase diagrams of, for example, strongly correlated materials such as heavy fermion compounds, where you have a very rich abundance of quantum phases, such as magnetic phases, superconductivity, and sort of a very clear transition from an antiferromagnetic to a Fermi liquid state, resulting in a quantum critical point here. And I will just basically give a little bit of a glimpse of that really twisted bilayer graphene might sort of contain similar type of physics in it. And of course, the other sort of a comparison goes into quantum Hall systems, where also like a very rich sequence of topological phases has been realized in twisted bilayer graphene, but also in other alternative twisted materials, one has realized also fractional quantum Hall phases that actually even persist down to zero magnetic field, which are basically topological in nature and do not need the high magnetic field. So, and basically a lot of sort of the open questions which are still persistent in these strongly correlated materials can now be also addressed in this Moiré materials platform, but with sort of novel capabilities, I would say, and sort of maybe trying to one can try to design alternative experiments that are not so directly possible in traditional systems. And this is just to give you sort of an overview of the different tuning knobs that we have available for twisted materials. So we can tune the twist angle and sort of tune the topology and the flatness of the bands. We have carrier density tuning knobs such as gates that can control the Fermi energy continuously. We can induce displacement fields that modify and flatten the band. We can induce layer stacking and alignment to different crystals, which can sort of change the symmetry and topology of the systems. We can also put them in different dielectric environments. Because they're two-dimensional, they can really, these dielectric environments can affect the electron-electron interactions quite dramatically. And so basically, really, this gives us, and sort of the abundance of the different materials that we have to play with gives us really novel experimental possibilities, such as, for example, in TMDs, one can realize the tunable Hubbard models in solid-state platforms. One can engineer flat bands and topological bands, and of course, the combination of these. Okay, so and basically, with these sort of capabilities, I will try to convince you that one can really now position Moiré materials somehow in the intermediate length scale between sort of traditional crystals such that host strongly correlated phases, such as the cuprates, where the interaction length is sort of defined by the lattice constant, which is usually in the orders of a few angstroms, and in between the sort of the optical lattices, which of course are synthetic sort of quantum simulators, where even though we deal with a much sort of larger artificial lattice here, one has extremely rich control knobs to manipulate the quantum phases in these materials. So, and I would argue that really Moiré materials can be somehow thought sort of at an intermediate length scale between those two systems, with also some capabilities that are either present in the crystals or in the optical lattices, but also some entirely new capabilities. Okay, so this is just a little bit the motivation and the introduction to what's going next, but let me just maybe give a sort of very slow glimpse over maybe for the people who are not so familiar with the field of two-dimensional materials. So of course, everything in this field, especially experimentally, started with sort of the extraction of single-layer graphene, which is basically this honeycomb lattice out of carbon atoms. This is basically this thinnest material that you can imagine. So you cannot create another two-dimensional lattice from thinner or lighter atoms than the carbon atoms. So it's really the thinnest material that you can synthesize. And also the technique with which it was synthesized with Scotch tape techniques, is truly remarkable. And the reason sort of graphene, I think, caught so much attention back then is because it, from the get-go, started to show very interesting and unexpected physics, such as the description of its electron bands with the Dirac equation, where basically electrons were thought to be as massless objects, similar to photons. So providing basically a possibility to study a relativistic physics in a condensed matter experiment. But then the other thing that is sort of quite remarkable about graphene that had extremely good materials properties. So the lattices that you sort of extract with the Scotch tape techniques are extremely clean, very sort of few defect states that you can imagine. And also the lattice is very strong. So basically, if you look at the sort of strength of this carbon lattice, you can really stretch it quite a bit without actually deforming it or without actually breaking it. And so these material properties really have a lot of sort of records. It also is sort of the material with the highest current density at room temperature and the highest mobility at room temperature. So it really also the material properties, besides the physics, were kind of remarkable. And this trick to extract these crystals, these monolayers, which we can, again, graphene can be extracted from graphite, but of course there are many other materials that sort of grow in this layered form. And in principle, you can right now find any type of condensed matter phenomena that you're interested in. It could be topology, it could be superconductivity, it could be magnetism, and so on. And you will find a van der Waals material that you can actually perform the same sort of assembly trick on, and you can extract single layers of these materials. and you can study, again, the type of physics you're interested in 2 dimensions. So and this was kind of been done for many years, very successfully by many of my colleagues. However, another sort of realization came very quickly, that not only do you have access to all of those 2-dimensional materials, but you have actually also the possibility to combine them and to hybridize electronic phases in them in a very efficient way, such that really much more possibilities are possible. And when I say assemble, I mean that you can also get this very simple columnation stamping technique, where you can actually extract various 2-dimensional material species one by one, and then you can sort of stamp them on top of one another, such that you can build sandwiches of all those materials, and you can really combine, let's say, different materials, starting from Dirac or topological insulators. You can choose superconductors, ferromagnets, and so on, and you can really combine them in these designer van der Waals stacks. And basically, the surprising thing when sort of people were developing this technique, so I was at Columbia in the group of Philip Kim, where Corey Dean and Jim Hone and Andrea Young, they were basically assembling the first van der Waals heterostructures like this. So the first thing, of course, we thought is that it might not give you anything high quality, right? It's a very sort of rudimentary technique. And the surprise was really that it can be quite high quality. So on a micrometer scale, not on a macroscopic scale, but on a micrometer scale, you find always regions which are extremely clean, where really here the interface between HBN, graphene, and MOS2 are extremely clean, and you don't find even disorder, or again, on a length scale of a few microns, that's possible. Okay, and then sort of last but not least, people slowly also realized that this new capability that you have here can also create Moiré superpotentials, Moiré interference patterns. That is also something which was not possible before. And let me just contrast it, this new capability really with traditional techniques. So the idea to, of course, make heterostructures and to combine materials and to build sort of these sandwiches of materials with different properties, this idea was not new, right? This has been done very successfully in the semiconductor industry since the 60s, I think. And this sort of involved very elaborate techniques that perform at extremely high vacuum, where you can really sprinkle one single atom of a certain atomic species, and if you wait long enough, these single atoms assemble on a surface and form 2-dimensional layers of whatever material you were interested in. And of course, you can switch up the material species that you wanted. But this type of a typical assembly, which starts with single atoms, resulted in the fact that really these assembled layers, they inherited the crystallographic orientation of the underlying material that were grown on. So here in van der Waals materials, because we start not with atoms, but we start with crystals, so each 2-dimensional layer is already like a preformed crystal. We really have that freedom to now twist and rotate them and to sort of really very precisely create these superpotentials that form the Moiré superlattice. Okay, so let me just walk you through how we go from single layer graphene to twisted bilayer graphene. So basically, we can start with just a single honeycomb lattice made out of graphene. Again, the unit cell is in the orders of angstroms. And if we basically just do the simple tight binding calculation, where we just really look at sort of the hopping from A to B atoms defined by gamma 0 here, we will find that really the band structure is defined by these Dirac cones. Again, they're protected by symmetry, so there's really this one point in which they're touching, and the bands are basically linear in between. And basically, you have two K points in the Brillouin zone. You have K and K prime points where these Dirac points sit. Okay, so what happens now if we put just a second layer of graphene on top of it? So again, this is also a system which you naturally find when you exfoliate devices. This is naturally occurring AB stacked bilayer graphene, where the top lattice is slightly misplaced on the bottom lattice, such that one of the carbon atoms here sits now in the middle of the hexagon. And now, of course, if we do the time binding, there are many hopping parameters that we need to sort of take account that sort of connect the layers and allow interlayer hopping between them. And this interlayer hopping already modified the band structure quite a bit. So if you look at sort of the dispersion close to the charge neutrality point, it's not anymore protected and linear. You can actually gap it out by introducing an interlayer potential. And it's hyperbolic. So the formula that describes this, it's not, you cannot approximate it with a linear. It's really a hyperbolic dispersion here. Okay, and so basically, if we now start twisting the material, what we actually achieve is some sort of oscillation, a length scale over which these hopping parameters vary, right? So whereas sort of in AB bilayer these hopping parameters are set for the entire sort of size of the device. In these twisted materials, of course, these hopping parameters, they vary spatially with the periodicity of the Moiré superpotential. And we can actually define regions where the system can be rather approximated with AA stacking. So if I look sort of in the centers of these hexagons, it's more like AA stacking that is describing these. And then they smoothly transition into AB stacking and furthermore. Okay, so this superpotential also gives you a height profile variation that can also not be neglected. So it's not just a geometric interference, but it really has some corrugations on top of the unit cell. And in general, again, this sort of twist also displaces the two brilliant zones between top and bottom layer. And this super periodicity creates novel mini brilliant zones that basically arise here in the corners that if we construct them between the two brilliant zones. So we have actually two independent mini brilliant zones because they're far apart in K-space. We can treat them most of the time independently. Okay, so and then if one sort of looks at sort of a system like this, then there was an intuitive way to sort of describe the band structure of those materials. This was done by Bistritz and McDonald back in 2011, so way before actually experiments have produced the twisted bilayer. These guys have predicted sort of the effect of such a moiré on the band structure. And they basically constructed this Bistritz and McDonald model, where basically they introduced some some continuum terms that connect the two layers and basically sort of account for this smooth variation of the hopping potentials or the hopping between the two layers. Okay, and so basically what these guys found is that this band structure that you get is highly twist angle dependent. And specifically, they defined angles for the rotation between the two layers, which they call the magic angles, where somehow the Fermi velocity really just went to zero. So you can see it here. So this is Fermi velocity as a function of twist angle. They found that really at small angles, the Fermi velocity just somehow drops to zero. And this is best visualized if I now sort of use this image here from one of Pablo Herrera's early work, where they actually made a video of the twist angle dependence of this Bistritz and McDonald model. And so what you can notice here for 3 degrees twist angle, the band structure looks basically just like single layer graphene. So basically you see these Dirac cones, you see this linear band dispersion, you see that there's no the Dirac cones are protected here, meaning that really for 3 degrees, everything behaves as it expected from graphene, and the layers can be thought of mostly decoupled from one another. And then you can also see that when you sort of start reducing this twist angle closer to zero, you strongly start renormalizing the band structure. And most sort of effectively, there is this one angle, which is called the magic angle at 1.1 degrees, when the bands really collapse onto one another and form basically extremely flat band structures. Okay, so basically this confirms that twist angle is a very rich tuning knob. And so basically in a single particle picture, again, just from the Bistritz and McDonald model, of course, people have now taken some corrugations and strain that is important in graphene into account. But basically the band structure we have in mind when we talk about, or a single particle band structure we have in mind when we talk about twisted bilayer graphene is this one, where we have isolated flat bands at sort of zero energy, which have a bandwidth of around 10 millielectron volts. This is a reduction of bandwidth of around 3 orders of magnitude from the single layer graphene case. So these bands are 1,000 times flatter. And they're also separated by high energy gaps to some sort of more dispersive bands at higher energy. Okay, so basically this flatness, of course, means that Fermi velocity is very small, kinetic energy is very small, and this basically creates immediately a platform where electron interactions can be the dominant term in your Hamiltonian. So U larger than T can be realized just from the flatness of the bands here. And another very important aspect is, as I said, there are these mini Brillouin zones, which are sort of created due to the twisting. Actually, these two independent Brillouin zones, each of them originates from this same K valley on the top and bottom layer. So this mini Brillouin zone contains the Berry curvatures of the K point of the top layer and the K2 point of the top layer. Therefore, if you now sort of try to integrate the Berry phase in such a Brillouin zone, you actually don't get a vanishing result, right? So in single layer graphene, K gives you a positive Berry curvature, K prime gives you a negative Berry curvature. If you integrate it, they both cancel each other out. But here, these two Berry curvatures, they're basically of the same sign in each of those mini Brillouin zones. Therefore, the total Berry curvature you get here gives you a Chern number which is non-zero. And therefore, really, we have here those two effects. We have a platform to induce strong correlations because U can be larger than T. And on top of that, the bands are topological. So we have this rare combination when we can actually study strongly interacting topology in these systems. OK, so let me now, after this introduction, let me now be a little bit more experimental. So I just want to highlight a couple of sort of experimental signatures here. So of course, when you sort of make devices, it's kind of tedious to make devices. It's hard to hit the magic angle directly. So basically, over the years, we had to sort of improve the fabrication protocols. So for example, we edge clamp devices. We sort of remove bubbles that appear when you sort of glue these layers together, which gives us a sort of much more reliable stability and allowing us to really lock the twist angle at exactly 1.1 degrees. Then recently, we also started to sort of very deliberately image all of the devices. So right now, all of the devices that we make in our group, we sort of image them with microscopy, with torsion force microscopy. This is like a friction technique where the needle is sort of resolving the friction on the layers. And you can see sort of really on a micrometer scale, we can resolve this moiré. We can also resolve super moiré structures here. And also recently, we incorporated this scanning microwave impedance microscopy technique, which can also image through the HBN. So even in encapsulated, HBN-encapsulated transport devices, if we keep the HBN fit enough, we can actually resolve this moiré superstructure, and we can really know exactly what is sort of the moiré looks like in the transport device. Okay, so then very popular techniques are also STM. So this is an STM image, scanning tunneling microscopy image of such a device. As you can see, if you wouldn't know the length scale here, you might mistake each sort of periodic point here as a atom. However, really each point here is this AA moiré site, so it's actually tens of nanometers in size. And really, you can sort of image like micrometer scale objects here. And if you do fabrication well, then you will find that this periodicity can be quite homogeneous over this length scale. And then, of course, once you have such a device, what you want to really probe as a first step is, of course, the band structure. And this was done, this can be imaged, for example, by nano-ARPAS, by angle resolved photo emission spectroscopy, where here you can actually resolve these band gaps between the flat and the dispersive bands, and you can resolve also the flat band regions, which sort of this dark cloud here. So the resolution is not like perfect, but also you can resolve sort of this folding of the Fermi surfaces and so on. Okay, so now having this type of devices, one sort of preferred technique in my group, but also usually the technique that is the first to probe devices where once you sort of made them. So one sort of very first technique is transport. And this is like an image of a typical transport device we used in the past. So it's in this whole bar geometry. that allows us to measure longitudinal resistance at the same time the whole resistance of the devices, so we can measure a sort of voltage laterally, but also perpendicular to the current flow direction. And also what's really important is the devices are typically encapsulated in these dielectric environments. So we use this HBN here to encapsulate the devices for quality reasons, so it gives us the best sort of quality and structural stability of the device. But second on, very important, most of the time we place also metallic layers very close to the device, such as in this case graphite, can be also, but it also can be gold, which basically allows us now to use voltage to inject carriers into twisted bilayer graphene. So this parallel plate capacitor configuration gives us basically a tuning knob to measure the devices with the precision of your voltmeter as a function of the Fermi energy, right? So it allows us to completely fill and completely empty these flat bands and really take entire phase diagram as a function of the Fermi energy of the system. Again, something which, if you would do it with crystals, something which would take you the growth of many crystals with various doping levels. Here, you can really use the tunability of these devices to create entire phase diagrams of this. And so here is basically such phase diagrams as a temperature-dependent and filling-dependent resistivity measurement. So here, really what we measure is Rxx, so this longitudinal resistance, as a function of temperature and as a function of filling. And filling here is again related to the carrier injection in the system, or in other words, to the Fermi energy in the system. And the filling factor that we define here is basically related to how many electrons or holes do we inject into each individual Moiré unit cell. And because in graphene we have this fourfold degeneracy of valley and spin, we can really fill 4 electrons into the conduction band. We can fill 4 holes into the valence band. And basically, each integer filling here corresponds to some sort of integer number of particles per Moiré unit cell. Okay, so what you see here in this phase diagram is that really a lot of, first of all, the resistance changes many orders of magnitude just when you sweep the gate. And in particular, at low temperatures, at integer fillings, we see a number of insulating states appearing. So those are those insulating states here, 2, 3, -2 here, which basically we understand as some sort of mod-like correlated insulator, where again, because the U can be bigger than T here, at integer filling, we might localize electrons and form Hubbard bands, which give us these correlated insulators. Then actually at higher temperatures, if I look here how these correlated insulators translate to higher temperatures, actually there's also a Pomeranchuk effect observed, which is basically indicative of some sort of spin-like ordering at higher temperatures. So it's really effect which becomes stronger at higher temperatures somehow. And then if we dope the correlated insulators here, we can actually observe superconducting states in many cases, such as here, as you can see, there is really a superconducting dome developing here between -2 and -3, where resistance drops to 0, and it has typically a TC of something like a 1 Kelvin. So it's by far, of course, not a high temperature phase. And then also what's interesting, what is sort of shown here at the bottom, is that if you look at now the dependence of the resistivity as a function of temperature, and we sort of extract the exponent here. So we look at the power law of the R versus T behavior, you will find that it's sort of most of the phase diagram, we find a power law behavior of 1. So the resistivity here scales with a linear slope. However, there are like phase transitions also sort of in this linear in T resistivity. So for example, closer to charge neutrality point, we tend to see some T square behavior and definitely not a linear T behavior. And then everything else is basically governed by this linear T behavior. And we sort of discuss this metallic phases in sort of non-Fermi liquid-like context, potentially it's something that one can relate to a strange metal. Okay, so now having sort of shown you the phenomenology of this, let me also go a little bit beyond the sort of single particle picture in terms of theory. So I showed you the Bistritz and McDonald model band structure here, and now I just want to discuss what's a potential way. It's probably not the only way because it's not a settled issue yet, but it's one of the most elegant ways, I think, to think how you can actually think of these bands now if you introduce some sort of interactions. Okay, and so in here basically is the Bistritz and McDonald model that I showed you before. And actually what you find if you sort of look closely at this Bistritz and McDonald model is that the regions which are of the band which are extremely flat, where really the electrons are very, very slow and like in principle to localize and are heavy. And then the regions actually here at the gamma point where the dispersion is not completely gone, right? So here you can see there's still leftover dispersion in the bands. And these carriers are not so light, not so heavy. They're actually still light and still very conducting. And basically this sort of motivated this topological heavy fermion model, which was recently implemented by Gida Sonka and Andrei Bernovic, which kind of found a basis transformation to decouple those carriers, right? So those two types of carriers that are very heavy and they're very light, to decouple them, and they basically performed a basis transformation where they were able to show that really you can think of the system as sort of perfectly flat F electron bands and still dispersive C electron bands that are coexistent in the system. And basically if they turn on the hybridization of these C and F electrons, they can actually obtain exactly the Bistritz and McDonald model. Right? And then basically directly map those two problems from one another. Okay, so basically a picture unfolds, again, this topological heavy fermion picture that in principle you can start analyzing the F electron that sort of are slow and like to localize on the lattice sites and the C electrons in a separate way, somehow interacting with one another. And just one word I want to say, so the reason actually these C electrons are still somehow present in the system and they don't really flatten out here is actually because of topological obstruction. So because the bands are topological, it's really impossible to completely kill these dispersive bands, these topological bands. They have to be there by sort of dictated by the topology of the system. Okay, so and basically now, once we have those many different, so two types of electrons in the system, one can of course try to break the interaction terms a little bit apart from one another. So basically one can write the effective Hamiltonian, which is H0 here for the single particle pace, and then you can include Coulomb repulsion only of the F electrons. You can include Coulomb repulsion only of C electrons, Coulomb repulsion of C and F, and you can also implement some exchange interaction between the C and F. And basically what really was, I think, one of the most important results of this topological heavy fermion model, you could also now apply this type of Hamiltonian and try to calculate dynamical mean field theory calculations that give you really the spectrally broadened Hubbard bands here. And so basically if you include Hubbard here, you first split on a single particle level the F bands. And then if you, again, perform DMFT and sort of also hybridize the C and F, the typical bands or spectral functions that you get here look the following, where you can see, so somehow the interactions here, they split the Hubbard bands apart. These Hubbard bands are highly spectrally broadened. But however, you don't form necessarily an insulator between those bands because there are still these dispersive bands in the way, right? So these dispersive bands are still there, and therefore basically how to think of such a spectral function is that you have really have to take into account both of those contributions. So of course our transport properties are still defined by these dispersive C bands, but they're sort of, because the Fermi energy is here at 0, right? So transport properties are defined by the dispersive C bands. However, these Hubbard bands, they can form local moments that can also, because of their, they can also be very strong scattering centers. Basically they can give a lot of sort of fluctuations and scattering for the C electrons. So the C electrons can very strongly interact with these local moments that are in the Hubbard bands. Okay, so basically take home here is really that we have to think of the transport properties in the presence of these strong background of fluctuating local moments. The typical dispersions that we get are somehow, I would say the word mod semi-metals. They're not mod insulators, but they're rather semi-metallic in nature. And then, of course, one has to really think hard about how these C and F electrons can interact. So, of course, they can scatter very efficiently. Of course, in principle, there could be, or there should be, a Kondo interaction between them. And so this is now sort of all sort of in the process of being understood. Okay, so this is still a lot of open questions related to sort of thinking about twisted biolographene from this sort of theoretical background. Basically, I think one sort of cumulative phase diagram that I would now try to sort of paint here is that really that we understand these semi-metallic phases at high energies that we, high temperatures that we see typically by this sort of mod semi-metal picture. And what is interesting, really, these metallic phases that we sort of see that are linear in temperature in temperature dependence, they're actually surrounding these mod semi-metals, and it will be interesting to further analyze whether somehow these fluctuations or the interaction of the C and F and the corresponding fluctuations could be sort of understood in this context here. And then at lower temperatures, actually, and so basically these semi-metal states, I think, I take them as sort of the first parent state from which I try to understand all the different phases. So the metallic phases here, one can try to understand from them, but also, again, at low temperatures, we have a lot of other things going on. So typically below 10 Kelvin is basically the temperature scale of our J. So as I said, Coulomb contribution is one thing, but then of course there's exchange interaction. So below 10 Kelvin, J, I think, takes over, and then you have a lot of phase transition. So the semi-metal here turns into a correlated insulator. So potentially this is due to some sort of ordering of the F electrons at low temperatures. Then, however, for example, the integers vary quite a bit in phenomenology. So whereas -2 here really turns from a semi-metal to an insulator, the filling factor 1 turns from a semi-metal to a Fermi liquid type of behavior. So this is, for example, one of those open questions that we have to understand the phase transitions here. And then, of course, superconductivity is a big one, right? And this is a completely different ballpark to now also try to understand superconductivity arising in the system. Okay, so a few words. So, okay, so this is really just the temperature-dependent part. This is mainly the part that contains the strong correlations between the electrons. But as I said, there's also a huge topological part to it. So, of course, topology had a role here because it sort of created the topological obstruction on the C bands that didn't allow it to gap out. But in principle, one can also work out the topological properties of this material a little bit more on the level of a single particle picture first. And just to give you an idea, so of course, for this matter, what's sort of more useful is the phase diagram as a function of magnetic field. Okay, so this is basically a typical high-quality phase diagram in magnetic field. So where, again, we still measure Rxx, but now as a function of magnetic field here on the x-axis. And so what you see here is really a very rich sequence of quantum Hall phases appearing, which are basically identified by these Landau fan lines. So each of those lines is somehow a Landau level, if you want, that you can characterize. However, we and many other groups also discovered that many of these features here should not be thought directly as a sort of just quantum Hall-like lambda levels, but are really related to the topological properties of the underlying bands. And in particular, so we really, on different energy scales, different temperature scales, we could work out that there's a really rich sequence of Chern insulators originating from the different integer fillings here, which basically give you really Rxx equal to 0, Rxy, which is quantized to the corresponding Chern number. So there's really a rich sequence of Chern insulators appearing in the system. And very often, these Chern insulators, they just basically persist down to 0 temperature. So several groups observed really perfectly quantized quantum anomalous Hall states, basically at filling factor free, which you can actually switch with magnetic field. You can actually train them with magnetic field and sort of switch them in one direction or the other. And so these states, you can think them, you can think them as of orbital magnets, or you can really just think them as of Chern insulators, which basically just appear at 0 magnetic fields. So without any sort of quantum Hall physics, really just from the pure topological properties of them. Okay, so basically this type of observations can be, I think they're, first of all, I think they're much better understood at this point than the strongly correlated things that I was talking before. So here I think there is a lot of consensus how to think of these systems. And so basically one way to sort of break down this problem is to actually, there were many papers who sort of really took care of the sort of topological bands that you sort of can have in the system. And as I said, so again topology comes from these Barry curvatures that do not cancel out in the mini Brillouin zones. But actually, if you sort of want to sort of create sort of or think of the quantum numbers that form these Chern bands, you will find that actually you will have to sort of decompose the system into 8 different bands, each band corresponding to a quantum number, which is either spin, valley, or sublattice A or B degeneracy. So you have 8 quantum numbers here. And if you sort of construct the wave functions here, you will find that really, depending on the sort of combination of these quantum numbers, certain bands have a Chern number of -1, and certain bands give you a Chern number of +1. And if you do before you introduce some interactions into the system, you will find that really in the Bistritzer-McDonald model, these bands are actually all degenerate. So they appear exactly the same energy. They're not to distinguish between one another. And the total Chern number that you get is actually 0, right? So you have 4 bands with Chern number 1, 4 bands with a Chern number -1, and they're perfectly degenerate to one another. So basically, in order to observe them, you actually need to start breaking some symmetries, right? And so basically, how do you break symmetries? So again, you need to sort of gap out the system by breaking C2T symmetry. So how you do it, one simple way to do it is just to break down time reversal symmetry. So again, this is something you achieve in high magnetic field. And this is again related to the Chern numbers that I showed you before. So basically, you can really, by just the symmetry breaking of time reversal, you can explain these Chern insulators at high magnetic field. You can explain them just by valley polarized states. Okay, so basically, you basically create an imbalance between the bands sort of in the K point and the K prime point, and therefore all of these Chern states at high temperatures can be thought of these valley polarized states. And basically, the exact Chern number you get here of originating from each different filling is just really sort of related to the combinations that you can find to produce such a valley polarized state in the system. Okay, and actually at a 0 temperature, 0 magnetic field, you can see there is story becomes much more complicated. And really at zero field, there's much more that sort of much more different states that can be sort of constructed. So one of the sort of most prominent states that people talk about right now is intervalley coherent states, but these intervalley coherent states can be also much more complicated. So for example, IKS, Kekulé spiral states can be also constructed here, and they have been observed in STM, for example. Okay, and I think this sort of the platform or sort of the way you sort of theoretically address these states is basically from this chiral flat limit, which I think Antoine will still teach in some following lectures. Okay, so now let me move on. So now I think this is sort of the overview of what the current thinking of twisted bilayer graphene. I think there's tons of open questions still. Hierarchy of correlated insulators not yet understood. We observe a pseudo gap and potentially a quantum critical point, but we have not worked it out in much detail yet. Nature of strange metal phase, pairing symmetry of the superconducting state, where here in the group of Preden-Rouleau, some experiments are going to decipher the pairing symmetry of the states. So I think a lot of those open questions are still there, and people need to continue working on this to figure them out. And of course, one other sort of thing is improved and easier assembly of twisted bilayer graphene devices is also something which has to go along the way with this. And with this, let me just shift over the last 15 minutes to some outlook and outlook. And here is basically some sort of overview of other material species that people have been implementing over the last couple of years. So again, twisted bilayer graphene was the first such system where Moiré gave you a flat band and interacting topology and so on. But of course, meanwhile, people have realized that really all those other materials that I've been introducing, they also in principle can be implemented for this trick, right? So first of all, in the graphene field, they're not just bilayers, but also trilayers, 4 layers, 5 layers that were implemented in this way. Then in TMDs, so again in these semiconducting materials, there has been also a lot of effort to study twisted systems, and one of the most remarkable results which came out from the field of TMDs is that you can twist MOT2 also to 4 degrees, something like that, and you can produce fractional Chern insulators, right? So you can produce the analog of fractional quantum Hall state at 0 magnetic field, which is really I would say it's the first completely new phase that has come out of twisted out of this Moiré material business, because in graphene, I mean, we have superconductivity, we have Chern insulators, and so on. So many phases that are known to exist in other systems. Here, FCIs, really, this is something which currently has not been observed in other systems other than Moiré. And then also, like a big effort is now also put in also to understand, for example, rhombohedral graphene, which is sort of ABC stacked analog without any twisting, where also by electrostatic gate engineering one can induce flat bands, and also these systems show very rich abundance of quantum phases. Okay, so taking this as a motivation, also like one outlook. So of course we were asking our theory colleagues quite often, so what other materials are there? So what other materials are worth twisting? And here, just to give you a glimpse of what a potential approach could be. So this is a paper, again, from the group of Andrzej Bernovic. So they basically asked themselves this question, and they developed sort of a high throughput algorithm to identify potentially promising and interesting other material species. So they looked at sort of whether these materials can be clean, single crystals, gate tunable, whether they have simple enough band structures to be able to worth looking into it. And they also classified these different material species also by lattice symmetries, so hexagonal, square, rectangular. So all of the materials that I showed you before were all hexagonal so far, so nobody has studied Moiré in square or rectangular lattices. All the materials that I showed you before had Fermi pockets at the K valleys, but of course you can think of materials with gamma and M-point valley structures, Fermi surfaces. You can also think of material with spin-orbit coupling that is not negligible, unlike graphene and so on. So basically, you really try to look at all the material ingredients. And just to give you one example, and this is what we are currently begin to work on. So for example, you can some of those materials that we found interesting, SNS2, hafnium S2, gallium telluride, and so on. And so basically, our theory colleagues calculated the twisted band structures now. So those are now twisted band structures with 3.9 degrees between SNS2, zirconium S2. And you can see what they find is really first of all, indeed, you can create very flat bands from all of those materials. Actually, many times you will find that the Fermi pockets don't sit in the K points, but in the M points here, for example. Okay, so if you are interested, so there's sort of many theoretical predictions. So, for example, these materials have they're also materials of a Kagome momentum lattice, and also these guys predict Luttinger liquids, spin liquids, and so on in these materials. So, would be interesting to see what nucleates really in experiments later on. But in terms of experiments, I want to say is that I think what many groups are doing now, because it's really a vast phase space now of different material species to cover. So I think what I found interesting is, for example, here at the Brookhaven National Laboratory, they built a fully automated setup to construct those devices, where they have basically in such an environment here, in a glove box environment, they have sort of a robotic system that allows you to immediately exfoliate, catalog, librarize, stack, and sort of do some structural analysis of such devices. So I would imagine that if you really would be serious to try to cover a small fraction of the space there, such sort of devices will be probably quite useful going forward. And so talking about the automation and maybe sort of really an alternative assembly of these devices, there has been also quite a lot of progress, and I found this one sort of development, which was introduced by the group of Shahalalani a few years ago, quite fascinating. So in order to not just make devices in the normal way, where you just basically stack the devices together, you encode one single twist angle per device. They thought of how can we maybe measure entire phase diagrams as a function of twist angle, right? And use a twist angle really as a dynamical tuning knob, similar sort of in style what I said with the gate, right? So our gates reduced the necessity of doping each individual crystal. So here also, what if we sort of get rid of the necessity to ingrain a single twist angle in a device? And so the idea was that you separate the two layers, actually. So you put one of the layers on a movable tip, an AFM tip, for example. You put the other one on a twistable substrate. And you can basically just come and probe your crystal like that, and you can dynamically rotate the substrate underneath it. Okay, and so basically one way to position this type of tool, so this type of tool can first of all assemble the moiré dynamically, and at the same time, because you can implement some sort of interrogation technique, for example, tunneling probe and so on, you can actually measure also the device at the very same time. Okay, so and maybe I'll try to convince you that really such a technique now we discuss sort of in the context of a tool that combines ARPAS-like and STM-like properties. So STM-like because can use tunneling as a measurement probe, and it can sort of spatially vary the different locations that it can have. Of course, it does not have atomic resolution because the tip is much bigger, but it has some sort of spatial interrogation properties. And then ARPAS, because I will show you in a second, it can really resolve the band structure and the momentum space of the underlying material. And however, this technique is fully compatible with millikelvin temperatures, with high magnetic fields. Its energy resolution is only limited by the tunneling probe that we implement, so it's purely electronic and can go well below 100 micro eV, I'm sure. And so basically, this technique could potentially also give us access to things that cannot be so easily implemented by or resolved by ARPAS. Okay, so this is basically just a little bit demonstration of a room temperature tool like that. So this is a typical QTM tip. So we implement these pyramids to transfer some graphene on top. And so if you image such a graphene tip, so you can do AFM imaging here, usually we create the tip such that there's a really large plateau, something like 200 by 200 nanometers. and this plateau can be very, very flat. Okay, and then basically we can basically position this tip and act it as a tunneling probe. And just sort of a proof of principle, we also have now low temperature setup. So again, this whole QTM business is compatible with, again, millikelvin temperatures and high magnetic fields. So we have now a setup which can go up to 911 Tesla and 10 millikelvin magnetic fields. And here is some sort of first sort of scanning of such a QTM setup that we have here. Okay, and so just to get a little bit more in the detail of really how the measurement works is here. So usually this is a cross-section, tunneling cross-section that we use in our devices. So again, you see here the tip, the graphene tip here on the top. It sits on a cushion of some graphite and HBN and top of this pyramid. And then on the substrate, you can see some also crystal, could be graphene or multilayer graphene, a HBN tunneling barrier, and B, basically bring those two surfaces in contact with one another, and we can inject through this bivoltage tunneling current across the system. Okay, and so here what the sort of tunneling or the bias voltage, what it does, so again, through the electrostatics, you can basically show that the tunneling does two things. That first of all, the voltage does two things. First, it sort of capacitively acts on the underlying material, so it actually raises the Fermi energy of the sample and lowers the Fermi energy of the tip. So it really has this function that it shifts the Fermi energies of both samples and tips. Therefore, the bias voltage encodes energy resolution in itself because it's related to the Fermi energy shift. And the second thing is, if we now look at the twist, what the twist actually does, it separates the Fermi surfaces. It separates them in K-space, and therefore really the twist angle acts on the momentum mismatch in the K zone. So it really separates in the K-space the Brillouin zones, and of course for small angles, K is just proportional to theta, right? So this theta really contains a momentum resolution in itself. Okay, so this is some data on tunneling from a single layer graphene into another single layer graphene. And so this is IV, the IDV second derivative of it. And if you sort of are familiar with the band structure of graphene, if you're familiar looking at Dirac cones and so on, you might already guess that really you can read out from this type of images, you can already read out the band structure of the graphene because you have these really linear lines here that appear in the measurement. Okay, and so basically, in order to understand more specifically, and I'm almost done, so just 2 more minutes. So to understand these lines more specifically, really one has to look at momentum and energy resolved tunneling transitions. And so one can basically understand this line as some sort of onset transition where momentum match in the different Dirac cones. And one can understand these hourglass shaped also from the band structure of graphene where these transitions basically run in parallel from one another. And also in some recent work, we have used really the resolution of the QTM to actually also show some small nonlinearities appearing in the Dirac spectrum as a result of some electron-electron interaction, basically screening of electrons. So this technique is very, very sensitive to really record some very small deviations in the band structure. And so here, this is the last slide. Really, I just want to show you that really we can also apply it to ABC, ABA, ABC trilayers. We can apply it to displacement fields. And quite often, I would say we get a really nice resolution of these features, which are really limited just only by electronics and the quality of our tunneling substrates, and not, again, like in ARPAS, by some surface properties and the resolution of the experiment. And with this, I want to sort of wrap up. So basically, where do I see sort of the field of QTM also moving is that really it could be useful to sort of more explore the vast landscape of different twisted materials. Recently also groups like in Weizmann or at Yale They have also worked out that really with the QTM, you can resolve the superconducting order parameter directly from the QTM spectra, because again, you have this momentum resolution. And I think what is really encouraging, so Shahal Ilani's group, again, he was the first to start this QTM field. He was also really, for the first time, able to, with the QTM, to resolve the strongly interacting flat bands in a twisted biolographene. So they could really show this picture of a mod semi-metal that I was showing before. They could really resolve it in their QTM measurements. So with this, thanks a lot for your attention.